Okay, so welcome. We'll start with proposition 17. So proposition 17 says, in any triangle, two angles taken together in any manner, just meaning any two angles, are less than two right angles. So if we have a triangle ABC, so that is okay, so obviously it's symmetric with respect to the various choices, so we'll just prove one of them. Okay, so what we're going to prove is that the angles ABC, BCA so taken together are less than two right angles. For extending BC to D, since ACD is the exterior angle of the triangle ABC, we have that it is greater than ABC. And that was proposition 16 from last time. Okay, well, let the angle ACB be added to each. That is, so we have that ACD is greater than ABC, and we're going to add ACB to both. Well, then this shows that ACD together with ACB is greater than ABC with BCA. That's by one of the common notions, I forget which, right? But ACD, ACB is equal to two right angles. That's by proposition 13. Okay, which is what we wanted to show. Right, we showed that this is less than ACD, ACB, which is two right angles, which is what I claimed in the beginning. Right, your turn, Kenneth.
Cool. So proposition 18. So proposition 18 says that if you have any triangle, the greater size obtains the greater angle. So actually, in this case, the statement there is much shorter than than the diagram. So for any triangle, so I'll write it. For any triangle, the greater side subtends the greater angle. Okay, so I'm gonna try and use this new feature. I'm gonna draw a triangle ABC. Now my diagram is gonna be a lot bigger than I thought. ABC. Okay, so let ABC be a triangle if AC is greater than, say, AB, then the the opposite angles are also correspondingly one greater than the other. So angle ABC is greater. Am I making all those dots? Yeah, probably. Is greater than angle ACB. Okay, so the way we're gonna do this, I'm gonna just do the proof here. So I'm gonna let D be a point on AC such that AB is equal to AD. So put the point D here, and these line segments are the same. I'm going to join up the point B to D like this. Okay, so see we get an isosceles triangle here that we're going to reason with. And so this is possible by proposition 1.3. By proposition 1.3, you can do this. And also we assume that the line segment AC is greater than AB, right? So the point D will lie on the line between AC. Okay, so right. So now we have the fact that you have an isosceles triangle here. Now since I'm still on eraser, so since AD is equal to AB by construction, we have angles ADB.
There's actually a usage of proposition 5 here. At least my copy of the book doesn't cite proposition 5, but
oh yeah, I was just about to. Actually, no, my copy cites proposition. Wait, we have the same copy, right?
I'm looking at it. I actually have a different book that I'm usually looking at,
Oh,
not a PDF.
right. Oh, right, okay. Yeah, they use proposition 5. So ADB. So the base angle is ADB is equal to angle ABD. Right, I believe this is proposition 5. Right, and then we use the external angle business to get us the conclusion, right? So since angle ADB, right, so is an external angle to BDC, angle to triangle BDC. So I'll just mark these on the diagram. So ADB is this one, and the triangle we're talking about is this one, right? So that's the external angle to triangle BDC. We have from proposition 1.16 that the external angle is bigger than the opposite one, the internal angle. So we have angle ADB is greater than angle DCP. All right, so this is proposition 16. And so, right, and so we have this, so what we're trying to do, we're trying to show that ABC, right, is greater than ACB, right? So now we have, therefore, hopefully I can fit this here. Therefore, angle ABC is greater than angle ABD. This is equal to angle ADB, which is greater than angle ACB. Okay, so ABC, right, is greater than angle ABD because it's ABD is part of ABC. And we've shown earlier that ABC and ABD are the same. I'll just mark these here because of the isosceles triangle business. Oh, crap. That's not good. Can we undo?
Yeah, just undo the little circly icon at the top.
Yeah, I'm clicking on undo. It doesn't.
You can't-
Oh, no.
You can't
You
undo the
can't
erasing.
Oh, okay, let me.
Oh, right. Okay, don't worry about
No.
it.
So I'll draw it back. It's too bad. Right? So we have the line here, and then we have the line here, and then we have the hilarious line here. Hopefully, I've redrawn it correctly, and I have to write the words back because the undoing killed the text.
We actually had a bit of an argument about whether we wanted to implement undo erasing next, and Billy just won that argument, I guess.
I was just thinking that.
Okay.
This is ADB greater than angle ACB. Okay, so get back to what I was saying. That these two angles are isosceles triangles, right? They're the same. And of course, ADB being bigger than ACB was the external angle argument by proposition 1.16. So that's what we wanted to show. Okay, cool. So that's proposition 18.
Great. Okay. So I'll move over to this board here. So I think we'll just only have time for proposition 19. Okay, so proposition 19 says in any triangle, the greater angle is subtended by the greater side. This word subtend, I looked it up earlier, so it has sort of the first part, sub, under, tend, from stretch, right? So it's the angle which is stretched when you try and look at one side of a triangle, right? So if you imagine your eye here looking, and then this angle here is what is stretched in your view by this side. I thought that was quite interesting.
That's cool. I never knew this.
Yeah, it's funny. I after high school geometry, I guess I never used this word again, so it's not actually a very familiar word to me.
Yeah.
Okay, so what does this say? Well, let ABC have angle ABC greater than BCA. Okay, so let's consider the following diagram. Okay, so we've got angle ABC and angle BCA. And considering them as drawn, they have the sort of desired relationship. So the claim is that AC is greater than AB. Right? AC, well, ABC being the angle subtended by the side AC, right? So the greater angle is subtended by the greater side, in this case, AC. Well, it's a proof by contradiction. If not, then AC is either equal to AB or less. Now they can't be equal. AC is not equal to AB. Well, if AC was equal to AB, then by proposition 5, the angles would have to be the same. Which is not true by hypothesis. Okay, so they're not equal. Neither is AC less than AB. For if it were, ABC would have to be less by what Kenneth just said than ACB. And that's proposition 18. Well, if AC can't be equal to AB and it can't be less, then it must be greater. All right, so that's proposition 19.
I reckon we could do 20.
Yeah, I reckon we can do it. Let's go.
Cool. All right. So 20 goes like this. Ooh. Okay. So proposition 20. So for any triangle that have two sides, where two sides are greater, well, sorry, any triangle has two sides greater than the sum of the two sides greater than the remaining side. Basically, triangle inequality, right? So for any triangle, the sum of two sides, or any two sides, are greater than the remaining side. Yeah, so now we're starting to prove some things that we might have seen in everyday mathematics. We'll draw a triangle, ABC. Okay, so ABC. All right. So yeah, so we're going to show that AB. So given triangle ABC, right, we're going to show that AB and AC are greater than BC. Okay, so proof. Okay, so we're going to extend, hopefully this time with these lines, my diagram will still fit. So we're going to extend this line here up to there, and we're going to join up the point to C. And the definition of this this point here, D, is such that these two are the same. Right, so what we're going to do, we're going to extend ABA to BD such that BA is equal to AD. Okay, so we can do this by proposition 1.3. Then the angle ADC is equal to angle DCA. So mark these. ADC is here.
I think there's a little bit of a logical gap there, right? So the common notions say you can extend BA to a line, and proposition 1.3 says you can construct a line from A that has the same length as BA, but it doesn't necessarily lie on a straight line with BA. So you have to cut off from the straight line extending BA something using that line you construct at A. Right? I mean, that's trivial,
Yeah,
but
yeah.
I guess it's not strictly speaking what proposition 3 lets you do. Maybe there should be there's kind of a missing proposition there somewhere.
Yeah, I mean, I would have thought that. I didn't go back and check this statement. I just thought, you draw a circle and then you cut it at D, right?
Right, yeah.
Because they do this extension of lines business, right? That happens a lot, right? You extend this line in the same direction, and then I don't know whether we've done this before. We must have done this before, right?
Yeah, I don't remember noticing this before, but you can start to feel Euclid chafing at the bit to leave some details to the reader at this point, right? Like, I don't know. I feel like this is the first instance where I'm like, yeah, he's going to start leaving stuff out soon,
Yeah,
right?
yeah.
Or like little combinations of existing things like this.
Ooh, I think I made a mistake. Actually, this is my mistake. I'm going to try and erase this so that it doesn't. I think the assumption is wrong. I want that AD is equal to AC, not AB. So we're gonna change this to these two AC. Yeah, because otherwise, this isosceles triangle business just doesn't work, right? So the conclusion is that we want the constructed triangle DAC to be isosceles, or DA is equal to AC by assumption. Then the base angles ADC is going to be equal to DAC, right? And this is proposition 1.5, right? Proposition 1.5, and right. So now. Get this back. So now angle DCB is greater than the angle DCA, all right, which was equal to ADC from above. So by proposition 1.19, BD is greater than. I think I would write it out like you've been doing. BD is greater than BC, right? Because a larger angle subtends the larger side. That's what 19 says, right? But BD is equal, BD is equal to the sum of AB and AC, so we are done. Yeah, so this is nice, right? We construct a new triangle such that one of the sides is the sum of the two sides of the original triangle, and then we use proposition 1.19 to conclude that this side, this new side, which is the sum of the two sides, is larger than one of the other sides, or the missing side, using the fact that larger angles subtend the larger side.
Yeah, this is cool. I really like
this.
this.
That's a nice proof.
Yeah. Cool. All right, we did it. 4.
Yeah, cool. Just in time.
All right.
Very nice.